So this talk is partly based on what I'm doing with my collaborator, Ricardo. And I have to say some things just to set the stage. Yeah. So I think that most of us here are philosophers. And well, the thing about we philosophers is that we like to think of ourselves as engaged, in a timeless, selfless quest for truth, right? We like to think of ourselves as seeking, if not necessarily attaining, truths which are universal and atemporal, and therefore they hold independently of the conditions under which they were obtained. Yeah? And this conceit that we have is actually not new, because after all, philosophy began when Thales of Miletus dared to lift his eyes from the path beneath his feet to the skies, to the heavens, to the stars that shine forever on everyone, in the search for timeless truth. But Thales paid a price for his disinterest. He lost his footing and fell into a ditch. And an old woman that was accompanying him mocked him, saying, "How do you think that you are going to understand the heavens if you don't know what your own feet are doing?" And Thales's pride was perhaps more hurt than his body, but most injured of all, I suspect, was his investigation of the cosmic order, because few stars are visible from the bottom of a ditch. Now, I say this because I want to suggest that Thales was not the only philosopher, not the only investigator of nature who have lost their footing badly, so that their search for truth has been impeded. I mentioned that in connection with this. This is the title of a very famous paper in mathematical physics, and it is representative of a view that has permeated the literature for decades, for over a century. I'll give you more examples. Take Max Humer in his widely read book, The Conceptual Development of Quantum Mechanics. He says, the quantum conditions were introduced as formal prescriptions without theoretical justification. So they were just a guess, justified by their empirical fruitfulness. Thomas Kuhn, in his book on the origin of the quantum theory, says something very similar. He says, the quantum hypothesis entered as an assumption whose physical basis remained obscure. Another example, Dahigal, in his widely read book, From C Numbers to Q Numbers, the quantum conditions appeared as independent prescriptions, simply imposed upon classical mechanics. Why? Unclear. George Mackey, now going further, talking about the canonical commutation relations, talking about canonical quantization, he said, simple and elegant as this is, canonical quantization appears at first sight to be quite arbitrary and ad hoc. It is difficult to understand how anyone could have guessed it. And finally, to give one last representative example, Landman, in his long paper on deformation quantization, he says, it has to be stated from the outset that, like the entire classical quantum interface, the nature of quantization is not yet well understood. So what's going on here, to put it in simple terms, is that people have the impression that this rule that was introduced by Planck just became this mysterious rule, which became this mysterious rule. Now we know that there are different ways, different techniques to quantize, but at the end of the day, we arrive at the same conclusion. And so the impression that we have, that people have, is that the founding fathers, they were special people that had a direct line with the gods of physics, you know, who just opened the skies and handed down the quantization rules to them. And this is something that the famous physicist John Wheeler could not accept. He used to insist that he could just not believe that the quantum was just handed down from the heavens. He used to insist, and given the importance of this is, you know, it's just unacceptable that this most fundamental concept of the most fundamental theory that we have is something that feels mysterious to us. So he used to insist on the importance of this question: how come the quantum? And I would like to suggest that the reason that quantization has appeared mysterious to us is that we have lost our footing. That the reason why quantization has appeared mysterious to us is that we have been looking at it from too narrow a point of view, you know, like Thales from the bottom of the ditch. I'd like to say that quantization is not, well, and I'm going to do that. And I'm going to answer that question. I'd like to suggest today that if that is the case, if that is the problem, then the way to solve it is to recover our footing. And this quote by Mach, I like to use it to represent what is my style of doing work on foundations of physics, to integrate it with critical historians. Generally, historians, they like to look at very specialized topics in very narrow periods of time. But this is not what we philosophers are generally interested in, right? We are generally interested in the big picture. We want to see how everything hangs together. We want to see what carves the thing at its joint. And I want to say that by following this approach, I'm then going to say, I'm going to answer this question. I'm going to give you an answer to this question. I'm going to say that quantization is not a mystery, that it actually follows from very deep and general physical principles. And when Eugene invited me to this talk, to give this talk, to come here to give to this workshop, I remember that he said something like, "Oh, I have this crazy idea that that physics is at the most fundamental level based on equilibrium consideration." You said something like that. And so if we take it to be the case that the quantum theory is the most fundamental theory that we have, one way of putting what I'm going to show today is I'm going to show that Eugene is right. But to get to that conclusion, we'll have to take a road that is rarely taken in foundational discussions. And so I'm going to just ask you to walk with me, to think with me. And this time we will watch our feet. Okay, but before we can take down the road, we can go down the road, we have to remove the things that have been obstructing our view. We have to clear the path. We have to get out of our head what has been the standard story of how the quantum theory began. The standard story is that Quantization was introduced in physics by Planck in 1900 in an ad hoc way. It was just a move to save us from the ultraviolet catastrophe. And the thing is that things cannot possibly have happened in this way. Was Planck aware of the radiation distribution law, which Rayleigh had derived as a necessary consequence of classical physics? Most authors enter this question in the affirmative and describe Planck's introduction of quanta as his response to the challenge of the crisis brought about by the disagreement between classical theory and experimental results, and by the internal failure of classical theory as expressed in the ultraviolet catastrophe. But as a matter of fact, there was no such crisis prior to 1900, or perhaps one should say there was no awareness of such a crisis. All of Planck's work on black body radiation prior to December 1900 was done without the benefit of the knowledge of just what classical physics did imply for this problem. And Klein was telling us this in the 60s. We should hear warning bells here already. You see that Klein is talking about awareness here, yeah? So for him, it was not that the Rayleigh gene was not inevitable in 1900. It was just people were not aware of it. It was a psychological thing, a sociological thing. In his paper, Klein talks about the tight classical web that Rayleigh had woven. But let's think things through. If the Rayleigh genes law was inevitable according to classical physics in 1900, then people would not have believed, as they did from 1896 to 1900, that the correct black body radiation law was Wien's law. If the Rayleigh genes law was inevitable according to classical physics in 1900, then Rayleigh himself would not have proposed the Rayleigh genes law as just an effective law, possibly valid for the long wavelength. So you see, Klein, in that paper, Klein does not appreciate, he doesn't seem even to note that what we call today classical limit, that is a construction that came only later. And Klein also doesn't explain, when's this change of awareness on the part of the scientific community that he's talking about here. He doesn't explain how it can be that people were not aware of the ultraviolet catastrophe in 1900, but after 1908, everyone was aware of it. He just says this and leaves the whole thing in the fog. But there's one thing that Klein cannot afford not to do, which is to tell us, well, if Planck was not aware of the Rayleigh genes law, then why did he introduce quantization? If Planck did not introduce quantization to save us from the ultraviolet catastrophe, then what in the world was he doing? And Klein's answer is that Planck didn't know what he was doing. Planck was just confused. According to Klein, what happened is that Planck wanted to use statistical mechanics to derive the correct black body radiation law, but he was still learning it. And then there is this, in one paper by Boatman, there's a discretization technique that it's just a trick, yeah, to carry out the calculation. And what you have to do at the end of calculation is take the infinite limit. But Planck then misapplied the trick. He didn't take the limit, because in that way, he got the right law. So you see, according to Klein, we have to believe that the father of the quantum theory was not, the sharpest tool in the box. According to Klein, we have to believe that physicists were then ready to overthrow classical physics and rebuild the foundations of physics afresh because Max Planck introduced an ad hoc idea by mistake. And that is something that is just impossible to believe. And it's easy to show that that's just not true. Here's what Planck says. In the 1900 paper, just right after he derived the law. He said, now I shall make some remarks about the necessity of that deduction. He talks about the necessity of that deduction. The fact that the chosen energy element for a given group of resonators must be proportional to the frequency follows immediately from the extremely important Wien displacement law. So he's saying that E equals h nu follows from Wien's displacement law. So it's not an ad hoc idea, not a response to the ultraviolet catastrophe, not something that he borrowed from Boltzmann. It follows from Wien's displacement law. And the thing is that the Wien displacement law is a purely thermodynamic result. It's an equilibrium condition. So we know exactly where we have to look to understand E equals h nu. We know exactly where our road begins. It begins with Wien. Now you see, Wien started to work on black body radiation years before Planck did. And Wien's work served as a foundation for what Planck did. And Wien got to the Wien displacement law by first proving a theorem that today is half forgotten. And what I want to do now is discuss this theorem with you. So the setting is, consider two boxes containing black body radiation, okay? And they are at the same macroscopic thermodynamic state. But they reach that state by two completely different processes. In one box, the radiation reached that state by a dynamical process, by exchanging energy with matter, okay? In the other box, that same thermodynamic state was reached without coupling it to matter. Yeah, you just make an infinitely slow adiabatic transformation, deformation of the wall. This is the setting. Now, here's what the theorem says. The theorem says that if there are no perpetual motion machines, then thermodynamics restricts not only the macroscopic state, but the microscopic state. The theorem says that if there are no perpetual motion machines, then the states in each of these boxes have to be identical all the way down. They have to be the same, identical wavelength by wavelength. And the proof goes by contradiction. So Wien asks us first to assume that this is not the case. Assume that the macroscopic state is the same, but that microscopically the radiations in each of these boxes differ by some lambda. The energy densities differ by some lambda. And then you isolate the difference and you put a thin filter between these boxes that is going to transmit radiation only around that lambda and is going to reflect everything else. Okay? Now, energy density is related to pressure. This is something that Maxwell proved. Radiation makes a pressure. And so the difference in pressure is going to create a force. And you can use that force to do work. Remove the filter. You're back where you started. And no reservoir was cooled. No entropy has been dumped anywhere, but you did work. And you can use this system. You can use different color filters to just continue extracting work like that. So you can use this system to build a perpetual motion machine. And if you take to be the case that there are no perpetual motion machines, then we must conclude that the radiation that you reach by a dynamical process by equilibrating it with matter. And the thermodynamic, the states that you reach by an infinitely slow adiabatic transformation, these states are identical all the way down. They are identical wavelength by wavelength. And this has huge consequences. Because you see, we have just the radiation, equilibrium radiation, and that's radiation. We find the exact same equilibrium states that are available for dynamical exchange with matter in equilibrium. And then you see, if you want to know what are the equilibrium states that are available to exchange with matter, you don't need to look at the dynamical problem. You only need to look at the adiabatic transformation, because they will give you what are the equilibrium states. And now we know why Wien proved that theorem, because he had a dynamical problem to solve. What Wien wanted to do is he wanted to see how the spectrum of the radiation changes when you change the temperature of the emitting body. He wanted to find that curve that describes how the spectrum changes when you change the temperature of the emitting body. And this seems to be an extremely difficult dynamical problem. It seems that you would have to know, you'd have to have a theory of matter, a theory of the interaction between radiation and matter. But by the upshot of his theorem, he didn't have to know any of that. He could just put the radiation in a box and see what are the equilibrium states. And what he found is that what he proved immediately after is that you put the radiation in a box, you see how it behaves under an adiabatic transformation. And if the second law is not to be violated, then in this process, the ratio between the frequency and the temperature for each wavelength has to remain constant. It has to remain invariant. And because the process is adiabatic, we call it an adiabatic invariant. But we know that these guys here define the equilibrium state. They carved the equilibrium state space for black body radiation. So Wien then proved that the function that is going to give us how the spectrum changes when you change the temperature of the emitting body, that function must be a function of those adiabatic invariants. Okay, and that is Wien's displacement law. And I just remind you of its importance with this. E equals h nu follows from it. And so now we are halfway through. Now let me make a comment that I already mentioned this in another talk when I spoke about Planck. It's that, you can achieve a lot in life if one has obsession. Obsession is the key. And what secured Planck's place in history is that this guy was just obsessed with the second law. So looking at what Wien did, relating energy and temperature, he wanted to put the second law into the picture somehow. He wanted to see what was the relationship, not between energy and temperature, but between energy and entropy. And in order to do that, he used this thermodynamic relation here, which relates the three variables, and then found a corresponding restriction for the equilibrium state of black body radiation, now in terms of the entropy and the energy. And what he found is that the entropy of the radiation can depend on the energy only as a function of the invariant E over nu. And the way that he got to the correct black body radiation law is by postulating that such entropy function, the function that's going to depend on those invariants, is this one. And so you see how intimately connected quantization and statistics are. But that is a topic for another talk. Here I want to focus on quantization, and I want to remind you that, black body radiation is the radiation that is equivalent with the radiation equilibrium with matter in an enclosure. And if the adiabatic invariant E over mu carve the equilibrium state space for radiation, the equilibrium states of matter has to be carved by the same invariant structure. Okay? And now here's the thing. If you know to be the case that E equals h nu holds for monochromatic radiation, and I've just shown you that this has to be the case according to the second law, this has a dynamical consequence. The action of a monochromatic wave is precisely that adiabatic invariant. So we know not only that a monochromatic wave carries energy equals h nu, we know furthermore that a monochromatic wave carries one quantum of action. And we also know now from the side of matter that for any periodic system, like a harmonic oscillator, like an electron orbiting in an atom, the action, this is the stationarity condition. This is the equilibrium condition for that periodic system. And Boltzmann had proved that for periodic systems like this, there is a complete analogy between the action and the second law. He proved that this quantity here is an adiabatic invariant. And so we know that the action for a plane wave is an adiabatic invariant, and we know that the action for any periodic system is an adiabatic invariant. And now we can, and we know, well, we can ask now, what about the composite system? Yeah, you have a composite system that is composed by matter and radiation. And then you ask, well, what is the action of the composite system? It's going to be the sum. And this is constant, right? And now I can ask, well, what if I put the atom and the radiation in a box and I consider an adiabatic transformation? So first, take just the atom before it emits, and then it emits. And this is constant. Now I know exactly the magnitude of this invariant here. It's h. Yeah. And now if I iterate the process, I find that the action for the first system is going to be this. Oops. N going to be a constant. The constant defines the ground state. If you set it to 0, you'll recognize the Bohr-Sommerfeld quantization rule. If it's half, it's the rule for the harmonic oscillator. And so you see, quantization follows from coupling it with radiation and demanding equilibrium. And now we see, let me just, oops. So this is what I've just shown you. And so you see that this and this, which you recognize as the two big postulates of the old quantum theory, we generally think of them as two sides, as two independent things, but they're actually two sides of the same transaction. They're required by equilibrium consideration. And if that is the case, we can extract more information from this. Because you see, let me rewrite this like this. Let's consider a change in the action. Yeah, delta S. Yeah, I just took the difference. Now I multiply everything by omega. So this guy goes away. And this is this, right? So now I found the relationship between the mechanical frequency of the system and the electromagnetic frequency. I find that this is the relationship between a change in the quantum theoretical system, a change that I do not observe, how this change is related to the physics that I observe. Now, there's a lot of physics encoded in this. There are many detailed thermodynamic considerations that are used to justify why this is the case. The argument is due to Bohr. You see, this is going to be the frequency associated with a periodic motion and this is the frequency associated to. Remember that you can always decompose the radiation field into monochromatic rays, like this. So you see, this is the mechanical frequency, and this, and what the rule says, I hope I'm being clear. What the rule says is that this is the height of the jump, yeah? The ends denote the stationary states. The possible jumps are encoded in the harmonics. The possible jumps that are going to give transitions, and are going to give you emission of radiation, they are encoded in the harmonics of the motion of the periodic system. And this rule, which I ask you to note, follows from this equilibrium requirement. Bohr elevated it to the status of a principle. He called it the correspondence principle. And the historians say that this principle was so important for the development of quantum mechanics. Actually, quantum mechanics owes everything to this principle. And I'm going to show you one of the reasons why. We're almost there. So what we do is then we take the action again. There are just a few things more that I want to show you. So what is going on here is that I just wrote that x dot squared in terms of its Fourier decomposition. Yeah, so I just replace x dot by taking the derivative of that expression that I just erased. Okay. And because it's a product, then I have a double sum. Yeah. And I just told you the importance of the harmonics. This is why I put them in red to call your attention to it. And here, well, you have this. Let me just explain what's going on, because I think that there's a lot to learn just from looking at each step. So here you have this integral, and it turns out that this integral is zero only when, for all values of alpha, except when alpha equals minus k. And then when alpha equals minus k, the integral is just 2 pi over omega n. And this is how you get the 2 pi over here. And then you see that 1 of omega n just cancels. And you have k and minus k. And now to get from here to here, I want to make some terms appear. And then you do a trick. What you do, what's going on there is that here, I just multiply that thing by 1 twice. Okay, I multiply that by this, and then I just rearrange the terms. And so now I have the action written in terms of a product between x and p, written in Fourier decomposition, in terms of a Fourier decomposition. Okay. All right. Now, why I am doing this? The next step is to take the derivative. I take the derivative with respect to s, and then on this side, left-hand side, I have 1, of course. And here I have the derivative of this thing. And now let me explain to you why in the world I'm doing that. Classically speaking, energy, the action and the frequency are related in this way. And we know also this. Right? Let me rewrite the frequencies in the same way. So born in 24, he thought, okay, so here's a rule to transform a classical quantity into a quantum theoretical quantity. I'm going to generalize this. So he said that whenever I have a classically calculated quantity that looks like this, the trick to transform it into a quantum theoretical quantity is to replace it by this. You see, can you see that this is just a generalization of this? Okay. And here, I have exactly that. So what I want to do now is rewrite this differential, this classical quantity, as a quantum theoretical quantity. And what I get is that. So now I have a difference. Okay. But I know that my job is not done yet, because the quantity I'm taking the difference of, they are these Fourier decompositions of this classic of x and p. And I know what correspondence principle tells me that I have to use this to relate the physics, the motion of the quantum theoretical system that I do not observe with the physics that I observe. And the thing is that And I'm going to show you how we got to quantum mechanics, because this is exactly what Heisenberg did in 25. Here's what he got the Nobel Prize for applying this rule to that quantity. Because he wanted to know, okay, how I deal with that product. I have to be careful. And then what he did is this. Okay, he remembered that for 2 consecutive jumps in Bohr's two jumps. Conservation of energy implies in this, right? This jump, then this jump. And then he said, well, okay, this should be the rule for the sum. What about the product? Imagine that you have a quantity that looks like this. And this quantity is the product of 2 quantities, A and B. And then he said, well, by analogy, just by analogy with this case, the rule for the product should read like this. This is just the product rule to apply this rule for the correspondence principle. And if you do that there, we get this. Okay. And if you look really hard at this thing, after some time, you're going to recognize what's staring at you in the face. Because this is this. People recognize that these objects here, under multiplication, they behave like matrices. They do not commute. So this is this. And so you see now why, when arriving at this point, people just threw away the ladder, and just postulated that the dynamics must respect this thing. What we have done here literally is to quantize the action. This is literally a quantum of action. And we have quantized it by applying this rule, which is the consequence of equilibrium conditions. So in classical physics, we have one theory describing the motion of material particles, and we have one theory describing the motion of the electromagnetic field. And what black body radiation forced physicists to do is to face the question of what are the laws that govern their interaction. And what they found is that if the second law holds, if there are no perpetual motion machines, then not every conceivable interaction is physically possible, because equilibrium constrains the exchange of action. It quantizes it. And so mechanics had to be quantized to accommodate this restriction. And what was found is that the way to do that, the way to modify mechanics in that way, to generalize it to accommodate this equilibrium restriction, is by doing this. And so if quantization had appeared mysterious to us, it is less so if we remember the path by which we came. Wheeler, I said in the beginning, he used to insist on this question because he could not believe that the quantum rules was just handed down from the heavens. He used precisely this expression. And he believed that the answer would turn out to be surprisingly simple. He used to say that when we had it, we would look at the answer and say, wow, but of course this is it. I mean, how could it be otherwise? And to think about it, what I have just shown you is that the quantum comes from answering this question. The quantum comes from imposing that the dynamics of composite systems satisfy equilibrium conditions. And if we think about it, if equilibrium constrains interaction, if equilibrium constrains dynamics, then one can think, well, indeed, how can it be otherwise? And that's what I had to say. Thank you.
Thank you. Thank you very much. This is a lot. I look forward to going more carefully through the details of the long involved story. Thanks a lot. Don?
Okay. Yeah, thanks a lot. And I look forward to going through the details of this long involved story because, yeah, I think you're absolutely right. It was much more a guided process of theory construction than will be often. I missed something. This is a very basic question. I missed something early on in your story, which was when you're talking about Planck. Where did the quantization come in? Because you gave us the Wien displacement law. And the Wien displacement law is satisfied by Wien's law and the Rayleigh-Jeans law. So by itself, it doesn't give you quantization. And that quote from Planck seemed to be saying, if we're going to quantize the energy, then E over nu has to be a constant. But why should we quantize the energy at all?
No. That E equals h nu. That E over nu should be a constant. That by itself follows just by rewriting Wien's displacement law in a different way. This is actually in Planck's paper, in Planck's 1901.
I understand. So if I have a quantum of energy, E, then E over nu has to be a constant. I understand that, yes. But why should I have a quantum of energy in the first place?
So you are saying that my argument is inversing the.
I guess no. I guess missed something because I felt like Wien's displacement law by itself doesn't entail quantization because it's satisfied by Wien's law and the Rayleigh-Jeans law. So where did the quantization come in? That's the question. Where does the quantum of energy come in?
I skipped that part of the details of Planck's derivation. But if we impose that that radiation is coupled with a finite number of degrees of freedom, if you impose a finite number of degrees of freedom, then quantization follows. This is also in Planck's paper.
Okay, I have to.
And then if you take n to infinity, that's when you have.
Okay, so I didn't miss anything. It was a step.
To choose which bit to emphasize.
Yeah, hey, thank you. That was super interesting. I really enjoyed it. And I also look forward to that. I have a question about the details that I'm sure I'll better understand when I read it in print. But So when you go through all this, through the derivation, and you take us from displacement to the correspondence rule to the quantization, I guess it's a purely historiographical question, right? Like, what are these derivations? So in the sense that, are those derivations that exist in this way in the historical record? Is it sort of a rational reconstruction? Because we had there were parts of the presentation when you talked about the displacement law in the beginning, we were literally following the derivation of Wien and others. And then later, I think I just lost track whether these are actual derivations done or whether this is a way that you reconstruct how we get from the correspondence principle to the quantization. So if you could say a little bit about this
You mean this last bit?
I guess everything that's on the right side of the on the right side of the board from my perspective.
This
Yeah,
this
yeah. Everything on the right side. Yeah.
yeah. So this
yeah, who's applying this? And so is it what are the papers like? Who's applying this? Or is it like you sort of simplifying for us like a much more complicated argument that is occurring over several papers? But is it Bohr, etc.? Yeah, that's the question. Just the historical context is all I'm asking about.
So this reconstruction, it is in a paper that I published with Ricardo. You cannot find it in the foundational paper on matrix mechanics. You cannot find these steps explicitly like this. They do this in 3 steps, which in themselves are unintelligible. But if you just fill in the details, beginning, middle, conclusion, this is exactly what I showed you.
Yeah, that was my question. So it's in the matrix mechanics paper. Okay, thank you.
Thanks. It was incredible. So I have a question, but Wheeler at one point said that H. Planck was like the highlight of a quantum formula or a quantum equation. He was aware about the quantization because it seems to me that this is the highlight of when an equation is a quantized version of it, because you pressure a lot the point where is quantum mechanics came from. Yes.
I mean,
Yes, but in his famous hit from bit paper, he said that H bar is the highlight mark of quantum mechanics, but it seems more that when you try to quantize in this way, you have what he's trying to express, and it's not a bit or something like metaphysical of what Wheeler had in mind, but it's just this mathematical tree. Yeah, and do you think he was aware of it or?
Of this derivation.
Yeah.
As far as I know, it has been reconstructed explicitly like this, with each step carefully laid out for the first time in the paper that I published last year with Ricardo. I could not, otherwise, yeah. Because it is really hidden. It is really hidden in the details of that paper. And I guess that these guys did not worry about making everything explicit, because these ingredients here, when you assume that the community just is aware of what you're talking about, and then you just simplify the steps, and then after 100 years, we are no longer familiar with the basic ingredients, and then things just seem mysterious to us. And then we really did a lot of work in trying to understand what was hidden under the surface in those papers, and then we got this derivation. It is in that dual action paper that I mentioned before to you on the past. Yeah, thanks.
Thanks so much for the. Okay, thanks so much for the talk. Okay, so I have a question that's pretty basic and about the earlier kind of context. So I'm thinking about how to understand people's critiques of Planck, and I'm wondering, like, I see the story, but this is quite a bit after when Planck is like giving a it seems like he's maybe giving a phenomenological kind of understanding, and then people come in and fill in the details and show how it follows. But I'm wondering if the folks that are kind of saying like not very charitable understandings of Planck are just thinking he didn't have the background to fill in the story. So does that make sense?
I'm not sure I'm understanding what you mean.
Like when you showed the kind of critiques of Planck,
Critiques of Planck?
yeah, like
In
color
the quotes that
yeah.
okay.
Yeah.
But yeah, this is another bit of the story. And then you wonder why people are reading it like that?
Well,
Yeah.
I'm wondering if maybe, yeah, I'm
Uh-huh.
wondering that the story comes, uh, yeah, oh, you just went through it. Yes. Oh, this,
Oh my God. Oh my God.
The
It's just
kind
right in the
quote.
beginning, right? And that was
okay.
motivation.
It comes up,
Uh-huh.
yeah, but yeah.
These
No,
things. Yeah.
no, I was thinking the Klein quote.
The Klein quote.
Like, Planck didn't have the whole story to fill in. So, I mean, I think that maybe this is a bit too harsh. But I'm wondering also if maybe like the story you've given us is reconstruction past when Planck was working on it. So yeah, I don't know how to balance these.
So I have a paper on that where I engaged with Klein's and other historians' work very in great detail. And one of the things, so Klein is trying to correct the standard story in a way because the standard story was about the ultraviolet catastrophe, right? And then what he says is that, well, there was no ultraviolet catastrophe really, so that cannot have been it. And then the way that he tries to rationalize this is that he notices that there is a book by Boatman where there is a discretization technique, and then he says, well, the resemblance can't have been a coincidence, Klein says. But as I said, the quote is very clear. And in one of his later paper, Klein says, well, Wien's displacement law played clearly a great role in what Planck did, but it's difficult to understand why, because that derivation involves, putting radiation in a box and seeing how it evolves, and it's difficult to see how the things are connected. So it seemed to me that Klein just did not get the facts straight because he didn't go far enough. Because then it takes a further step, what it's being with and doing and so on. And I think that this history was misunderstood for a long time because now we just simplify things by saying, well, the ultraviolet catastrophe, looking at the ultraviolet catastrophe. This is part of the story that I didn't mention. So I remarked when I was talking about this quote that Klein did not explain why it was the case that in 1900 there was no ultraviolet catastrophe, but after 1908 there was ultraviolet catastrophe. And the reason is this. The ultraviolet catastrophe follows from applying the equipartition theorem. And the equipartition theorem is a consequence of the kinetic theory of heat. And the kinetic theory of heat was just one model that people did not take very seriously around 1900. Planck, for example, didn't. But after 1908, after Perrin's experiments on Brownian motion, then the kinetic theory of heat was taken very seriously, and therefore its consequences. And so people would say, well, if atoms exist, then according to classical mechanics, they should obey the equipartition theorem. But they don't, right? But Planck had already found the solution by a different route. So I think that it is not just a later reconstruction, it was really misunderstanding on the part of the literature of what was really going on around those years. The second law played a much bigger role in the origin of the quantum theory than has been appreciated.
Works. Thank you. This is a great talk. I really enjoyed this talk. I have spoken to you about the book, The Trail of Blackbody Radiation, which I also read some time ago, but and it has a part of the story about two different ways to reach blackbody radiation law. One is a thermodynamic route that you've described, not in all the details, and the other is based on the Wien's displacement law. If I'm not, my memory is a bit rusty about the book. And the argument made in the book by Lemons et al. On the trail of blackbody radiation is that blackbody radiation is established via Boltzmann entropy and its form, but they don't go into the details of that you've come to as to why that must be the case. And I think one of the things that you mentioned in the talk is that thermodynamics not only restricts the macro state, but also the micro state. And that sort of leads to this particular form of quantization that we see here.
Yeah, they don't go into detail as far as I remember. They don't go. They don't go. Yeah.
So I'm wondering why, I mean, maybe you're not the book's author, but it's a very extensive survey of the literature of this topic. Why did they miss seeing that connection, despite them mentioning, at least in some detail, one of the chapters, a thermodynamic justification of the blackbody radiation? And why are people generally missed this quantization bit in the story?
Why?
Despite being so central and so important and being discussed, in different parts of the literature.
I can only speculate that people have not looked into the details carefully enough. I mean, that if you just look at what Wien did, it's, again, he sort of takes for granted that people are familiar with the problem that he's trying to solve. He doesn't really give an introduction justifying, explaining what he's doing, why he's doing what he's doing, because what he wants to do, he says, what he wants to do when he derives the Wien displacement law, he's justifying a remark by Boltzmann, because when Boltzmann derived the fourth power law, which we achieve the fourth power law just by integrating Planck's law, right? And we forget the fact that the integrated version that was derived by Boltzmann in 1884, just using thermodynamics. And he says, well, this holds for macroscopic. I'm just using macroscopic thermodynamics here, but I suspect that these conclusions must hold also for the microstate, but he could not prove. And then Wien did, even though if you read Wien's paper, he doesn't explain that that's what he's doing, or one of the things that he's doing. And you can ask, well, why I did this? Because I just could not, I had the feeling that I was not understanding everything, and I was going one step back, and then one step back, and then another step back until I felt that I had the big picture. But that is just something like my personal style of investigation.
I think a part of the story that people have missed, which is also linked to my talk, which is the connection between the equipartition theorem, the canonical state, and fluctuations and their particular structure. And all this.
But this was only after Einstein, right?
Yeah, it's only after Einstein. Yeah. Einstein and Szilard and the people who sort of tried to make this a bit more clear. And so because all this comes a bit late in the literature, maybe, to draw a story that goes all the way back to understanding the restriction of microstates, I think, one should take a holistic look at the literature in this part. I think there's something interesting that's going on, and
it's absolutely the case that what was behind Einstein's mind when he's led to those investigations on fluctuations and everything, it was these things.
Yeah, certainly. More to talk. Thanks.
maybe just a thought to share. So it's great talk. It's very many details I want to discuss in depth. But when listening to the story, I just keep myself distinguish like two aspects of the whole story. One is because by saying origin, we can mean different things, right? And one thing is why quantum, why quantum physics itself is discrete, is quantized in that sense. And then why we can have a formulation that can like apply the rule that like why there's like non-commutative algebra that we can construct out of the theory. Those are two different aspects. And in the first aspect, I think Planck and Einstein's work that really help us realize energy is discrete is very important. And realizing this, then the second story can come in, and then realizing everything's connected, like thermodynamics, like classical physics, poisson-like, and then symplectic structure can be applied and to derive the structure of like the algebra of quantum physics. Only if we realize like the work that Planck and Einstein and those people did to have the discrete of the spectrum. So that I agree that the aspect of thermodynamics and statistical mechanics play a very important role in formalizing to justifying the algebra of quantum physics. But it's different from saying, well, the very discrete nature of quantum physics comes from thermodynamics, because there's no such element in thermodynamics tells us particularly that the energy is discrete. Just does it make sense?
I'm not sure I understood the.
So I mean, just maybe to clarify that the meaning of origin.
The meaning of origin, yes.
It's the formulation of physics, right? That could be contribution from our understanding of and statistical mechanics. It's not that like the way that we understand quantum, understand like the net energy should be quantized is from. Does that make sense?
That was physically, that's where it comes from. The restriction that you get when you apply equilibrium conditions for coupled systems. In the way that so why do we now have these quantum rules and these non-commutative algebras and so on? What is the mystery what is the deeper physical principle that's behind everything? These are certain.
That's how you structure theory for quantum. That's not where the discrete is. That's from like experiment. That's from how we understand mathematics.
Yeah, I'm not sure.
That's a different. Sorry, actually, the idea of this like the discrete theory, like quantum, like the idea of having quantum theory as a discrete theory, versus the specific formulation of the quantum rule. Whether by explaining the origin of the quantum rule, you're also explaining the very idea of having a discrete micro.
Yes. And I try to clarify maybe in your talk, like you were suggesting in the second part, formalizing the thermodynamics and statistical physics plays a very important role that people don't realize before. In formalizing these systematic type formulation.
That's the last one. Right. Yeah. So maybe related to that, I wanted to clarify the sense of priority we're talking about here when we talk about equilibrium. Like I guess you have this nice ladder or like chain of equations. I'm not sure you can show that. Like near the end, right? You have this like
But that was just don't take that so.
No, well, I mean, that's why I want to clarify the based on the kind of picture, what kind of structure are we talking about here, right? Yeah, I guess I'll just jump into it.
With Thales looking at the sky.
No, well,
Yeah,
not yeah, I think I'm thinking about like this not Thales, I hope.
it's not what you had in mind. Which
Yeah, no, that was the right one. Yeah, that was the right one. The constellation. Yeah. So I was just wondering the kind of priority we're talking about here, right? So maybe Eugene question is it's more like or maybe I'm not sure. Eugene can clarify himself. But yeah, the question for me is like, in what sense does everything begin from equilibrium? Firstly, like is it like a to use the old distinction, like is it like a context of discovery kind of point, or is it like a context of justification kind of point? Yeah, like in what sense does everything hinge on equilibrium? Another way to phrase it would be, does this depend on the system being in thermodynamic equilibrium? In what sense does it depend on the system being in thermodynamic equilibrium? Because we might think now today that we don't think the commutator depends on the quantum system being in equilibrium. So in what sense does it depend
Um,
on it being equilibrium?
I guess that what this story is telling you is that where the quantum theory began with black body radiation, which is a system that is in equilibrium, and the quantum conditions were found that way. And the quantum theory is just a generalization to other systems that must, so that those conditions are still satisfied.
Right.
Yeah, in that sense.
Yeah, so it's like,
And my point is that having that road in mind just helps you understand the underlying physics behind this mathematics.
Great.
Yeah.
Yeah, no, I think it's great, and kind of relates to Miguel's point as well, right? We began with equilibrium systems, not necessarily that all physics just is equilibrium.
Yeah, no,
But
of course,
we begin with equilibrium, and then we
exactly,
how to work with it.
exactly,
No.
precisely.
Yeah, you can.
I just wanted to add that then, of course, you don't demand thermodynamic equilibrium for commutativity in quantum theory, because quantum theory is such a generic theory that encompasses not just equilibrium states, right? But so it's much more like Newtonian mechanics than anyway, yeah.
Yeah, the parallel with the lessons that you were making in your talk about Newtonian mechanics.
think that's-
Yeah,
yeah.
yeah, precisely.